So I'm going to tell you about the Einstein equation. This is the equation that describes gravity in our universe. But the equation is kind of complicated. So what I want to do instead is firstly just build up slowly with Newton's theory of gravity, which is quite old and a little bit out of date now, but has much simpler concepts, and then we'll move on to try and hopefully get to the Einstein equation. Okay, so in 1686, Newton gave us a formula for gravity, which is the following. So, formula for gravity, and it's a formula for the force. So it's given by the following equation. And the equation is very simple to understand. You have two objects. This, say, is the Sun, and this is the Earth. This has mass m1, and this has mass m2. And to compute the force, you multiply the masses together. You divide by the distance between them, and then there's some proportionality constant, which is it's called Newton's constant. It's just a number. It's some constant of nature. And what do you do with this? Well, you use Newton's other famous formula, which is F equals ma, and you plug that into this, and you get to understand the force between two objects, and therefore the acceleration between two objects. Okay. There's another formula I'm going to use just by analogy, which is very similar to this. In fact, it's almost identical to this. So this is due to Newton. And the other formula is due to a guy called Coulomb, and is the force, the electrostatic force between two charges. So electrostatic, and it's the following. So if you have two particles and they carry electric charge, the force between them is you take the charge of this particle, which is q1, you multiply by the charge of this particle, which is q2, and you divide by the distance squared between them. Okay? And then there's some overall constant, which it's got a slightly different name. It's 1 over 4 pi epsilon 0. The constant's in the bottom rather than at the top, but again, it's just some proportionality, some constant of nature. So this looks quite nice, right? They're basically exactly the same formulae, just where you've got masses here and charges here. So this is due to Coulomb. And I think from about 100 years later, maybe 1780s. And what would be really nice is if somehow, to tell you about modern physics, I could just write down a slightly different thing on the right-hand side. I can tell you what the force is due to various phenomena in nature. The trouble is we can't do that. Because force is kind of a concept buried in the 1680s, and it's just not the right way to think about physics. So we kind of, we use the word force all the time, right? There are 4 fundamental forces in nature and so on, but it's really just this archaic word that we should get rid of. So in fundamental physics, as we know it, there's really no concept of force. It's not what it's about. And so what I want to do is just explain why force is such an old-fashioned idea and why we have to move beyond it. Okay, so think about this formula. So this is the formula between two charges, so we'll take two charges here. And suppose that, okay, we'll take two charges, there's the force between them that's given by this formula. So let's say this is positive and this is negative, then they attract each other. Okay. Suppose that I take this charge and I move it very quickly to here. Okay. The question is, how does the force change? If you use this formula, you might think it's dead easy. All I do is I've increased the distance from this to this, so this number here gets bigger, which means the force gets smaller. Okay. That can't be the right answer, though. And it can't be the right answer because if I move this very quickly to here, then yes, the force ultimately has to get smaller, but it can't do it immediately because Einstein's special theory of relativity says nothing can travel faster than the speed of light. So somehow what's missing from these formulae is the fact that there has to be something that transmits the force from this particle to this particle. And that's true both for electricity and for gravity. And so what we have to do is really get rid of this idea of force completely and introduce new objects which transmit what's happening from this particle. And these new objects are called fields. So this was really Faraday's great contribution to theoretical physics, was to realize that spread everywhere throughout the universe, there are things called fields. He introduced the idea of electric fields and magnetic fields. And what happens is the following. This particle here is giving rise to electric fields. And this particle here feels that electric field and moves in response to it. That's what we call a force. When this particle moves, what it does is not instantaneously affect this particle, but it changes the way the electric fields are distributed. So as this particle moves, it'll give rise to a little ripple in the electric field, which propagates through space, actually at the speed of light, and finally affects this particle here. In fact, as it moves, it's much more complicated. As it moves, it doesn't just give rise to an electric field, it gives rise to a magnetic field. It actually gives off some what we call electromagnetic radiation, which is light. And so you have this very complicated effect where when this particle moves, all these fields are rippling and changing shape, and finally this particle feels that and moves in response to it. So it's not just a simple force, it's much more complicated than that. In this side here, this took a long time to figure out. This took like 200 years to figure out. But finally it was finished by a guy called Maxwell in the late 1800s, about 1860. And Maxwell realized he needed to replace this simple equation due to Coulomb with 4 equations that describe how the electric and magnetic fields respond not just to charges that are placed there, but also to moving charges. What happens if charges move? So he wrote down a series of 4 equations. I'll write them and I'll sort of vaguely explain what they are. Okay, so the 4 equations are... I feel really bad if this one's wrong. Oh, almost. Okay, I missed some. Okay, good. So what's going on here? We've introduced lots and lots of new objects. So the E and B are the electric and magnetic fields. So these are objects which exist at every point in space, and at every point in space the electric field is a vector that points somewhere. So at this point of space it points somewhere, at this point of space it has a different magnitude and a different direction. Same for the magnetic field. These weird upside down triangles are like calculus. It's basically a way of having differentiation. So this is like a derivative of the electric field, a derivative of the magnetic field. The same for this. This is derivative with respect to space, this is derivative with respect to time, and finally on the right hand side, this is what became of the charge. So this is not charge but charge density, it's charge per unit volume, and this is current, so this is moving charge. So these are the equations that describe this much more complicated setup of what happens when charges move and the electric and magnetic fields ripple. You know, they're not terribly complicated. There's 4 of them, but you know, they're some of the most amazing equations in physics in the sense that they capture everything we know about electricity and magnetism. I mean, absolutely everything is in this. Okay, so that's what's going on with electrostatics. What about for gravity? So all these same issues are there. If the sun was to move suddenly, the Earth would not feel the fact that the sun has moved immediately, but it would take some time to respond to this motion of the sun. So there has to be something like a field for gravity, just like these electric and magnetic fields, that ripples and changes in response to things moving. Okay. So that's what Einstein's equations do. They go beyond Newton's simple force formula, and they allow you to describe how gravity, well, they allow you to describe the effects of gravity when things are moving and not just sitting there. Okay. Einstein's really amazing insight is that rather than having to introduce new things, electric and magnetic fields, The analogous thing for gravity is something we already know about. It's just space and time itself. So what Einstein realized was that the analogous thing for electric and magnetic fields is space and time sort of warping and stretching and bending. So the way it works, Einstein's great insight, is that you have something heavy in space, and the analogous thing of giving rise to electric fields is that this thing heavy in space changes space and time. So there's a picture which I'll try to draw. Might be a bit rubbish. This is supposed to be a picture of flat space. Okay. Flat space with nothing in it. Einstein realized that if you take something heavy, like the sun, and you put it in this space, then space is not just a passive bystander. Background space, and in fact the background time, doesn't just sit there. It's malleable, and it responds to the fact that this heavy thing is sitting there. So the space actually will bend. Probably going to be a terrible picture. Like this. Good. So you're supposed to think about a dent in space-time here. And it's this dent in space-time which is the analogous thing to these electric and magnetic fields. So another particle, like say the Earth, which is smaller, sits in this, and when it moves, it feels the fact that space and time are bent and curved, and so rather than travelling in a straight line as it would in flat space, actually responds to this curvature of space-time and moves in a circle, or more precisely an ellipse, around the Sun, which is why the Earth orbits the Sun. The equation he wrote down is the analogous thing of this equation, which is on the left-hand side the fields, which is space and time, and on the right-hand side the analogous thing of the mass. Okay, so this is what Einstein's equations look like. Okay, and then there's something. I think it's this. Good. So, how to understand this? The first thing to say is that these are, well, roughly speaking, these are 4 equations. This looks like it's just one equation. It's not. This is actually 10 equations, all linked together. Okay. This side here describes the curvature of space and time. So in fact, rather than saying space and time, one of the lessons of Einstein's theory is that space and time can kind of warp into each other. So we just say that they're one object, space-time. And this thing here describes, well, what became of the masses. So this is mass density, mass per unit volume. But Einstein's other theory, special relativity, tells us E equals mc squared, which is energy is the same thing as mass. So this thing here is telling us about the energy distributed throughout space. So energy density. But on this side we had charge density and current, which was motion of charge. So this contains energy density, but also motion of energy, so energy moving, but that's what we call momentum. So this energy density and momentum. Okay, so that's the two sides. Let me try and explain a little more why there's 10 equations here. Okay. By the way, I should say that this is again just a constant. This is Newton's constant, 8 pi is 8 pi, and c is the speed of light. But it's just some overall constant. Actually, when we do physics, we always just set these constants equal to 1. So That's why I struggle to remember. But whenever you do, a professional physicist will always just set everything equal to 1, basically. Okay. Good. So, what's going on here? The reason these are 10 equations is because of these strange little Greek symbols which are sitting underneath everything. So this is the Greek letter mu, and this is the Greek letter nu. And in these equations, mu and nu are labels, and they take values 0, 1, 2, or 3. Okay. So the reason it takes values, well, it takes 4 different values is because we have 4 dimensions of space and time. So 3 dimensions of space are this way, and this way, and then there's the dimension of time, which is that. So this is space, and the 0 is time. And it's a little bit weird that we label it 0, 1, 2, 3 rather than 1, 2, 3, 4. It's just to remind us that time is a bit special, so we kind of label it as 0. Okay, so what does this mean? It means that mu and nu here, and here, should be replaced by these numbers. So, for example, one of the 10 equations is where these are replaced by 0 and 0. Okay. So this left-hand side here, where there's a zeros everywhere, is telling you about the slowing down of time, or the speeding up of time. And this is now energy. Energy is associated to the slowing down and the speeding up of time. Okay. Alternatively, I could replace this, there's another equation where these have 1s, or 2s, or 3s. And this equation is telling you about the stretching of space in the x direction. And it's related here not to energy now, but actually to pressure. The pressure that matter causes in the x direction. Alternatively, they don't have to be the same. So we could have 0, 1, 0, 1, and 0, 1. So now this is telling you how the stretching of time in the x direction gets rotated in, the stretching of time gets rotated into space in the x direction. So the mixing of space and time into themselves. And what's here is the momentum of matter in the x direction. So what that means is if you have a planet which is moving that way, then the motion of that planet will mix space in that direction with time and warp them together in a way which is described by this equation. So that's the Einstein equation. I should say that these equations for a physicist are very easy. I mean, we can solve these equations basically completely and understand everything that's in them. These equations are extremely hard. So we're a long way from being able to solve these equations in general. Even now we need enormous computers to try and understand what's hidden in these equations. And there's conferences every year where people tell us, where people find new solutions to these equations and get very excited about them. But there's no conferences about these equations. We just understand these equations.
Can I ask one question?
Yeah, please.
So, when you wrote down that the mu and the nu can take 0, 1, 2, 3,
yes.
4, and there's 10 equations, I'm like, okay, so you can have 0, 0, 1, 1, 2, 2, 3, 3, 0, 1, 0, 2, 0.
And it adds up to 16.
And adds up to more than 10.
Good.
Why is that?
That's right. So the way to think about it is to draw a matrix, actually. These are really matrix equations. So mu can take values 0, 1, 2, 3, and nu can take values 0, 1, 2, 3. And so for every element here, we've got an equation. The reason that there's 10 is because this is symmetric. So 0, 1 turns out to be exactly the same thing as 1, 0. So let's count. There's 1, 2, 3, 4, And then we don't double count because 0, 1 is the same thing as 1, 0. So there's 5, 6, 7, 8, 9, 10. And these equations are just exactly the same as these equations. That's where the 10 comes from.